Today is day 48 of daily LeetCode. We are back once again. Reflections on yesterday. We released the final installment in the movie in our trilogy. It was called Fry Time 3 Diff or Die. The outcome of the movie was a death because we actually couldn't finish the problem. The problem is right here. It's called reconstruct itinerary. So we need to find a way to figure this out going forward in the future. But like we said yesterday and the day before, there's a long backlog of review problems to do. So that's what we're going to be working through. I think we might just have to pause. I'm going to be honest, I think we just have to pause everything and just do review. Right? The backlog of review problems is just too large, and so it must be done. Necessary evil. But as they say, the greatest chance for knowledge is learning from our past mistakes. So we have to make sure we do that very well, and then hopefully in future problems we make less mistakes because we're learning from our previous mistakes. That being said, it is an unknown amount of cards that we have due today. We have longest substring without repeating characters to start. So that's definitely one thing we'd like to do. And then yeah, that's what we're going to start with. Yes, that would be what we're going to start with. Other than that, I mean, the Explorer card method has been going well. So we used to randomly do practice from a bunch of different topics. Now we're just doing topics based on specific areas. Right now we're on graphs, so we learned the union find data structure. We're working on the depth first search version of the card right now. Then we get to BFS and then Dijkstra's and then MSTs and so on. But that being said, I think the goal so far is to make sense of all of it. And the first thing we need to do is to get our house in order and make sure that the number of review problems to new problems is a good balance. Right now there's so much work to be done on review that I'm struggling on newer problems because I'm not osmosising enough information from the old problems. And so that's really the goal. And so hoping to learn from the previous problems so we can do future problems and get closer to being able to solve every problem. I think the other thing is that typically if you try to solve a problem, you struggle for a while and then you see the solution, then you can solve it. But then when you come back to it, you're actually unable to solve it. I think that's because struggle is a really good elaborative encoder. So when you're struggling on a problem for a long period of time, you can imagine it as a maze where you finding the exit to the maze is akin to solving the problem. Right? And when you try to solve the maze here first without looking at the solution, then you end up pretty much visiting the entire maze. So when you do see the solution, you're just like, oh yeah, I touched on this solution, on all of my previous attempts to get to the correct solution. I never got there, but you kind of explored the whole graph basically. When you look at the solution, it's like you can see the path, the shortest path through the graph, but it's just, it's not, doesn't stick in your brain as well. So that would be the goal. That being said, review is very difficult because it requires a lot of resistance to it requires a lot of being able to withstand monotony, because you know the correct answer, you know the solution, you know the constraints, you've read the problem, you've read the solution many times, but what you're really doing is excavating a little bit deeper for another gem, right? And so it's hard to do the due diligence on every problem when you already know the outcome, I guess. But that being said, the work must be done anyway. So we're going to, also make sure to join the Hyperbolic Coding Chamber Discord. Thousands of people are doing it every single day. We're on day 48. So that'd be pretty cool. Today's video is actually going to be the fourth. It's actually going to be part of a saga. This is the fourth video in the saga. This one's going to be called Fry Time. This one's going to be called Fry Time 4. Fry Time for the beginning, or no. Fry Time for the end is the beginning, because we're reviewing problems, and that's what's going to get us to the end. Also, make sure to join the Hyperbolic Coding Chamber Discord. Thousands of people joining every day. We have information from secret people like I'm Just That Guy. is insider information on all the top tech conglomerates as well as the Copy Ninja. So feel free to join. Easy tips. There's also a couple of codes you can type directly into your LeetCode, or IDE, and it's actually automatically going to instantiate an instance of GP3 and solve the problem. So you're going to want the information invaluable. To jump into it to start with longest substring without repeating characters. So to start, I'm going to take a picture of the notes from the last time I did this problem. So we have longest substring without repeating characters, and what I wrote for last notes was try for a linear time solution with a character array. The current solution that I usually use is a worst case time complexity of n squared. So let's read this problem. Given a string s, find the length of the longest substring without repeating characters. So if we're given s, right, our output is 3, right? And because the answer is A, B, C with the length of 3. A, B, C is the longest substring without repeating characters. Even if you go to the next subset of A, B, C, and then C, B, B isn't close because B, the second B is repeating. Then we have B, 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 right? The answer is B because the longest substring without repeating characters is just going to be the first character, which is B. Then we have P, W, W, K, W. The answer is W, K, E, the length of 3, right? It can't be P, W, W because the longest substring without repeating characters would be P, W, right? And then W, max there would be P, W, which is 2. Best we can do is W, K, E, right? Or K, E, W, both would give us a substring of 3. So that makes sense. So we can see that our constraints are that S can be 0, and since S can be 0, you want to be careful of that. And so what we can just do is say, hey, if S.length equals 0, let's return longest length. The length of the longest substring is going to be 0. So S consists of English letters, digits, symbols, and spaces, right? So I think to generate potential paths to get through this, I think this could be done with the sliding window pattern where we would have A, B, C, and so the sliding window pattern is just a pattern that allows us to visualize a window through a sequential data structure that allows us to keep track. We can do a lot of different things with it, but basically allows us to keep track of a subset of things within a sequential data structure. So we'd have A, B, C, right? Every time we add a character, we want to make sure that character doesn't already exist within our within our current window, right? When it does, we'll just restart, right? We'll move characters up to that character. So we add A to our window, then B, then C, then we add A. So we want to remove characters until we find A. So we end up removing this A here and adding this A to the front. Well, now we have B again, right? We remove characters until we find B. Now we have C, A, B. Now we have C again. We remove characters until we find C. And we see that the best we can do at each point is a length of 3. So one method of going about this is the sliding window pattern, which depending implementation, right, depending on imp, can have a time complexity of O of n squared. It's because you're iterating through the array once, and since you're iterating through the array once, to check whether or not a character already exists within the window can take linear time depending on the length of the substring or the window. So let's try for a linear time solution with a character array. So if we have a character array, what we could do, right, is imagine we have a character array, and this character array could have 128 spots, right? And this could be mainly to keep track of the ASCII range of 0 through 128, right? We could go up to 256 as well. And each index would map to a specific ASCII character. Now, I'm not actually certain what the first ASCII character is. We would know its number of occurrences, right? And then we can go all the way up to, I think, 65 or 64, which is actually A. And we would have one occurrence so far. So I think the goal with this method would be, if we iterate through the array, right? Iterate through the array, right? We'll say, hey, let's add an occurrence of 1 for our, let's add an occurrence of 1 in the array for our ASCII character, so we change it to 1, right? Then on the next iteration, right, while our current character's occurrence is greater than 1, right, so we'd go to B, right, so let's map this out. We'll have iteration through string, right, and we're going to say, hey, while our current occurrence of A, right, is greater than 1, right, and if we're looking for the longest substring without repeating characters, this would actually be, would actually mean that every character that is in our substring has an occurrence of 1. So what this array up here is actually going to represent, it would actually represent the occurrences in our current substring, basically. So if that's the case, then we could iterate through the string, right? And we'll say while A's occurrence is greater than 1, right? While awk of IDX greater than 1, right? What we're going to see is that A's occurrence is not greater than 1, right? So we can just say, hey, R sub IDX, right, plus equal 1. So now A would be actually set to 1. All right, then we go to B. We'll say, okay, while awk of IDX is greater than 1, well, B does not have an occurrence of, doesn't have a positive occurrence yet. So we're going to do R sub IDX plus 1, which is going to be B is now set to 1. C is going to be set to 1, right? And so what our array is going to look like so far is 1, 1, and 1. And then we'll get to A, and then we're going to say, okay, while awk of IDX is greater than, or while awk of IDX is greater than 1. Well, awk of IDX is actually greater than 1, right? Because we'll have A. And so what we're going to want to do is that we're actually going to have a left and a right pointer. And as we're iterating through the string, right, this is going to be while right, I guess while left is less than right. Left is less than right. While right is less than s dot length, right? We're going to say while awk of IDX is greater than 1, right? What we're going to want to do is actually shift our window, right? Because our left and right pointer are still going to, in a way, represent our sliding window. This is just sort of an optimization on top of that. So our left and right pointers are going to indicate the indices that we're actually working with. If it's going to indicate the indices that we're actually working with, then while awk of IDX is greater than 1, what we're going to want to do is actually say awk sub, or not awk, R sub left, right, minus equal. So we're going to do left, right? And so whenever we were able to add a character, right, it was that our right pointer was moving forward. So we're going to have right plus equal 1 here, right? But at the same time, whenever we remove a character, it's because we're decrementing, right? So our awk of, I guess, R sub IDX, we can change it. R sub IDX is greater than 1, right? No, it's going to be while R sub right is greater than 1, right? Because our current index is greater than 1, right? Now we want to remove characters, right, from the left-hand side All right, so we're going to iterate through the string from the left-hand side and remove characters until this is rectified, right? And so if left is starting at 0, we just got to C, right? So left starts at 0, right? We had our sliding window go through A, B, C. Right, we have 1, 1, 1 for each in this array. We can see up here. We get to A, right? And right, we're going to say, well, R sub right is greater than 1. So now I'm realizing we actually want this to happen before. It was like R sub right, R sub IDX, which is really R sub right plus equal 1, right? And then we say, well, R sub right is greater than 1, right? That's a problem. So our current window as it stands right now would actually be ABCA. And so what we're going to do is say, while R sub right is greater than 1, A is greater than 1, it's 2. We're actually going to do is do R sub left minus equal 1, right? Since we're starting at 0, we decrement A by 1, right? And then we want to do left plus equal 1 to move it forward, because now left would be at B. Left would be at B, right? And then we go to the next indice. We do right plus equal 1. We now go to B, right? We go say right is still less than index 0, 1, 2, 3, 0, 1, 2, 3, 4. 4 is still less than 8. 4 is still less than right 8. Right, we're going to say R sub right plus equal 1, which is going to be B. Right now we're going to say, well, R sub right is greater than 1 because we do have two B's. Right, we're going to do R sub left, right, minus equal 1 because we're iterating through the string and subtracting it from the array of occurrences. Right, we're going to subtract B by decreasing its indice. R sub right is now going to be equal to 1. Left plus equal 1. We're now going to be back at CAB. Add C. And we should be able to continue this over and over. Let's pretend, right, if we go from A to B to C, right? So we'll say our left is 0, right, and our right is equal to 0, 1, 2, right? And we go to the next iteration. R sub right plus equals 1, right? While R sub right is greater than 1, because A sub, in the array, if we subscript A with its character code, it's going to give us an occurrence of 2, right? We'd say, well, R sub right is greater than 1, which it is. R sub left minus equal 1, so we bring left equal to this index B. Left plus equals 1, right? And then right plus equals 1 to take us out of bounds. And right will no longer be less than s dot length, so we can actually stop. Right, but how do we know the length of the longest substring? Well, we have our range of indices, so left and right is actually going to store that information. So left is going to be at index 1, right? And right is going to be at index 0, 1, 2, 3. Right, it's going to be at 3. So if we do 3 minus 1, right, which would be our range, right? 3 minus 1, which would give us 2 plus 1. So we should be able to return 3, right, minus left plus 1. So let's try and implement this, right? We need to have our occurrence array, right? We'll just call it occur. It's going to be an empty array. We're going to populate it, right, with 128 indices, or just to cover as many ASCII values as we can. And we're going to say occur dot push 0 onto the array, just to get it started. Right, and then we're going to have our left and right pointers. Left is going to start at 0, right? And right is also going to start at 0. And then we'll run while right is less than s dot length, right? We'll do R sub right plus equals 1, which makes sense, right? And then we'll say, hey, while R sub, we want to change R to occur. We'll say while occur sub right is greater than 1, right? And that's an issue, but it shouldn't, because for A, when we start, it's going to be equal to 1, right? Then we're going to say right plus equals 1, right? And then right, which is 1, is still less than length, right? Occur sub right. But the problem is that if we do occur sub right, right is actually an index, And the way we're going to get the correct value in this array of occurrences is by using the ASCII value of the string. So we actually want is s sub right dot car code at 0 to give us the correct indice. And so I think we could do is say write car idx and do something like s sub right dot car code at 0 instead, and then replace s sub right dot car code at 0 with write car idx, and we'll do write car idx is greater than 1. Right, we're gonna have to do something similar for left, right? We'll say s sub left dot car code at 0 minus equal 1 to left plus equal 1, and then we can return right minus left plus 1. So let's try with a small example like pwweq. Left is going to start at 0, right's going to start at 0. 0 is less than 6. Right rdx is s sub right, which is 0, which is p dot car code at 0, which would be the ASCII value of p. And one thing I just realized we didn't consider is our input always going to be lowercase? Is another good question. And does two characters of different height, two different casings, does that count as a repeating character or not? But we'll check pwwkw 0, right? We're going to do s sub right dot car code at 0, which gives the car code for p, right? Increase p's occurrence. P's occurrence is not greater than 1, so we do right plus 1. Now we're at w, right? We increase the occurrence for w, right? Add 1 to it, and it's not greater than 1, so we keep going. Now we're at w again, right? We increase the occurrence for w, and we say, well, occur sub right car idx, because w's occurrence is greater than 0, it's equal to 2 right now. We do r sub s dot left, which is 0, right, dot car code at 0, which is p, minus equal 1. Then we do left plus equals 1. Is it still greater than 1? Then go for another one, right? We're now going to remove w. So w right here. Is it still greater than 1? It's not. Right plus 1. We're going to be at w. Add 1 for w. Add 1 for e. And the final thing so we should be good. The length of longest substring. We're going to want to make sure we keep track of that. So you let length equals negative infinity, and then at each iteration we're going to want to take the max, right? So we'll say if we're at pww, right, after we do once we're at w, you're at wk or pww, right, we're going to add that one character. Oh, we're not going to, we'll do, so we have pw, we start at 0, we have 0, 1, 2, right? Before we add that extra w, we only have pw, which means our current max would be 1 minus 0 plus 1, which would be 2, right? But then we do right plus equal 1. If we do it after, we don't really know that this extra w counts. We're going to want to do it before, so we'll say length is equal to the math.max, length and right minus left plus 1. Then we can return len. So let's try running that. We still had one occasion of r. So our first example, let's test with the remaining examples. Okay, so that's pretty good. And I would say our time complexity for this, and we have one constant time. We take a 128 operations to set up the array, the occurrence array, which would be all zeros. That could be constant time. Because for any arbitrarily large input, we're going to use 128 operations. From there, we do a linear iteration through the string, but we do a while to remove characters. And I think that at worst case scenario for this, right, is that we get to the end of the string and we have to we have many occurrences of the same left. Get to the end of the string and we have a duplicate character, but the character is right behind us basically, and so we'll have to iterate through the entirety of the string again to remove those occurrences until we get right, that occurrence back down to 1, but that would still be 2n. So in that case, I think the worst case would be 2n, which would be linear time and constant space, right, depending on the size of the input we want to allow, because 128 values in the array can't always fix everything in regards to uppercase, lowercase letters, uncommon Unicode characters like Japanese characters or anything else. 128 just is not a large enough array, so in that sense maybe we'd want to swap this out for something like a map where we could still get constant time lookup but could support many other strings. Above solution is sliding. Oh, so it is a sliding. It is an optimized sliding window. The above solution requires at most 2 n steps. In fact, it could be optimized to require only n steps instead of using a set to tell if a character exists or not. We could define a mapping of the characters to its index. Then we can skip the characters immediately when we found a repeated character. The reason is that if s sub j have a duplicate in the range I sub j exclusive with index j prime, we don't need to increase I little by little. We can skip all elements in the range I, comma j prime, and let I to be j prime plus 1 next directly. A little unclear. Oh, this is actually not what we did. So our approach seems a little bit different than actually what they did. Oh, right, so this is kind of closer to what we did. Right, and we got there, we said 2n would basically be equal to linear time. In the worst case, each character will be visited twice by I and j. Space complexity will be the minimum of m or n. Same as the previous approach, we need O of k space for the sliding window. K is the size of the set. Size of the set is upper bounded by the size of the string n, and the size of the character set or alphabet m, which is true. Right, and so to check if a character is already in the substring, we can scan the substring, which leads to n squared algorithm. But that's kind of what our original solution looked like, and it wasn't squared. By using a hash set as a sliding window, checking if a character in the current can be done in constant time. So this could be, our solution could be changed, right, to our previous solution, except use a set or hash map. Sliding window is a window slides its 2 boundaries to a certain direction. Example, if we slide I, comma j exclusive to the right by 1 element, then it becomes I plus 1, comma j plus 1. Back to our problem, we use hash set to store the characters in current window. Then we slide index j. So I think this makes sense. Things to consider for future nodes. Try for a linear solution with a character way. Let's try full event solution with a set or a map. Do a better explaining how sliding window pattern works, or how this version is an optimization. So update the notes there. So we do have some cards to do. So we'll do balanced binary tree. So given a binary tree, determine if it is height balanced. For this problem, a height balanced binary tree is defined as a binary tree in which the left and right subtrees of every node differ in height by no more than 1. So let's map this to our example. We have a binary tree to start of 3, and the height of its subtrees here would be 1, right? And we'd have a height here of 2. Now if we take the difference, as they say, the height differ in height by no more than 1, height of 3, wait a second. Oh no, this would be a height of 2. Yeah, height of 2, which I think refers to the number of edges basically. So we have a height of 1 versus a height of 2, and what we'll see is that 1 minus 2 is 1, so it's not greater than 1, so this is a balanced binary tree. For our second example, we can see that we have a root starting at 1, and our height here is 1, and our height here is 3. The difference here would be 2, which is definitely not a balanced binary tree. And we can also see that for an empty binary tree, we'd like us to return a value of true, because an empty binary tree is balanced. So just off the bat, we can say not root, right, then return true. Then from here, we'd like to make more sense of the problem. We know that the number of the values in the range can range from negative 10 to the 4 to positive 10 to the 4, and we know that nodes in the tree can be empty. We've handled the case when the nodes in the tree are empty. So if that's the case, I think there are 2 common traversal methods you can use for a binary tree. That would be depth first search and a level order traversal. And I'm thinking that the solution that makes the most sense here, just to generate some nice solutions, we want to know the height of each tree. So I think one thing that we could do is we could do a level order traversal, right? If we did a level order traversal augmented with a DFS, right? So we do a level order traversal with 3, 9, 20, 15, and 7, right? And then for each node, what we would do would run a depth first search algorithm, which would basically calculate the height for a particular subtree. So we could call that for both 9 and 20, both of our subtrees for 3, and it would give us a value of 1 and 2. Then we could take the abs of DFS1 minus DFS2, right? And if it's greater than 1, we want to return false. Otherwise, we'd like to return true, right? And then we could go between 9, right? Then we'd go to 9, right, and basically compare, run this height calculating algorithm for 9, right? And if it empty subtrees count for balance, so we'd return true here. Have the same for 20, it would have the same height, right? We'd run the same thing for 15, which give us true. 7 would be true as well. The time and space, the time complexity of an algorithm like this would actually be n squared, since we'd be visiting every node once with a level order traversal, and then visiting almost every node in the tree with the depth first search. We'd have n squared, and we'd have n squared space as well. Actually, no. Or maybe, yeah, because level order traversal takes at most n space in a queue, right? And so it's possible, right, if we're also going to be using recursion with a DFS, that for every particular node we would perform n operations, which would take n space on the call stack. So I would say space could also, time space would also be O of n squared. And I also think there's a secondary solution to this where we could do a depth first search down to a particular node, and as we're coming up we can just check the heights between nodes, but this sounds a bit more cumbersome and I haven't thought this method completely through. So let's try this version. And so what we'll do is a level order traversal. So that usually starts with a queue which has the root node to start within the array. We'll say while queue.length isn't empty, which means we still have work to do. We're going to pull off cur, which is going to be the first element in the queue, right? If cur exists, we'd like to do some work, right? And like we said, right, if, right, and we can call this h1, we'll say height of cur.left, right? And we'll call this the height of cur.right, and we'll say if the math.absolute value of h1 minus h2 is greater than 1, that's an issue, right? So we're going to return false, right? And if we make it past this point, right, it means their difference wasn't greater than 1, so we'd like to add their children onto the queue to also be processed next, right? But only if their children exist. So we'll say if cur.left, then we'll say q.push cur.left, and if we'll do cur.right exists, we'll do cur.right here. And then presumably if we make it all the way down here, we can return true. And then what would be remaining was that we'd have to implement this height function, which would take a node, right, which could be a tree node or null, and it's going to return a number. So if the node doesn't exist, we're actually just going to return 0. Now if the node does exist, what we'd like to do is calculate the maximum depth, and so what that's going to mean is we have to take the maximum of every node in the subtree, right? Because if we take the maximum depth of 2, right, it's not really, we don't want to only consider 3, right? We want to take the maximum of its 2 subtrees, right, which would actually be 2 here, right, plus the 1 at the top. So that being the case, at this point the node would exist. So since the node exists, what we'd like to do is return 1 plus the math.max of the height of node.left, right, and the height of node.right. And so if we think about this for a second, let's see if this makes sense. We want to calculate the height of, let's just say 3, right? 3 does exist, so we're going to return 1 plus the math.max of height of node left. Well, 9 does exist, so let's go and check its children, right? So return 1 plus the math.max of node.left. Well, node.left is empty, so we return 0. Right is empty, so we return 0. So we return 1 to 3. So now we have 1 plus the math.max of 1, or height.node right. So now we're working on 20. We go to 20, right? We take the height of 1 plus the height of the left. So 15, right, does exist, right? Both of its nodes are empty, so we return 1, right? So now we're at 20, we're saying return 1 plus the max of 1, right? Or the height of node right, which is also going to be 1 for 7. So the max of 1 or 1 is 1, plus 1 is 2, right? And we go back all the way up to 3, right? We're going to have to choose 1 plus the max of 1 or 2. We're going to take 2 and return 3 as our total height for 3. So it actually does make sense to start. And so let's see if this gets us an answer that makes sense. So that makes sense. And it does pass the cases. So I think that the time complexity of this would be n squared time. I'm wondering if it's possible to create a linear time solution to this, but I'm not actually quite certain. And I think space complexity would also be n squared. Oh, so it looks like there is a So there is a linear time solution. I think that's what we said earlier. If you go down, check your way up. And that is a better way to do it. So maybe next time we'll try for a linear time solution. But they also had a log of n solution, which is interesting. Was it this one? Oh, it was this one. First, we define a function height such that any node p within tree T, -1 if p is an empty subtree or null, 1 plus the max height of either of the subtrees otherwise. Now we have a method for determining the height of a tree. All that remains is to compare the height of every node's children. The height of every node's child. A tree T rooted at R is balanced if and only if the height of its children are within 1 of each other. And the subtrees at each child are also balanced. Therefore, we can compare the 2 child subtrees' heights, then recurse on each one. I see. So I think I see what they're getting at here. You recursively obtain the height of a tree, right? But they're using a depth. Wait a second. It's balanced. So what they're doing here is if we start at the top node, if it is the root null, well, let's copy this code and see if it makes how it makes sense. So we actually have a description here. So we have an example 1, right? And so we're saying is balanced. So does 3 exist? Well, does 3 not exist? So then root equals null. It does exist, right? So we go down to return the height of both of these trees. So the height of left is going to be 1, right? And the height of this one is going to be 2, right? If we subtract them and it's less than 2, right? Because they have to be within 1 of each other. You could also do the, oh, no, wait. They're checking for truth here instead of false. Checking for truth instead of false here. So if the absolute value of the difference, 2 minus 1, is less than 2, then that's good. But if we did 3 minus 1, we'd get 2, which would be a problem. So that means we're good, right? And if that's the case, then they call it for the left and right subtrees. Then we go to 9, right? And root left does exist, right? And then we try to take the height of both trees, but it gets -1. And 0 minus 0 is still less than 2, so this returns true, right? This would also return true for 20, at least 20's first call. Is mine also linear time? Then how is this also linear time? Finds is not also linear time because we visit the whole tree. For each node, we do n operations, but it also looks like they're doing n operations for each node here. Therefore, we can compare the two child subtrees. Then recurse on each one. So this is interesting. I think we're doing very similar things here. But I thought my solution might be n squared, and I'm pretty sure it is because we're visiting every node, potentially every node in the tree, given a node, or potentially every node in the left and right subtree of a node, given a node to start. But when I'm reading their code, it looks like they're just doing a depth first search using the same height function we did and propagating it with this balanced. So I wonder. That one is interesting. I feel like I need to take a better look at that one. So we have missing number. So given an array nums containing n distinct numbers in the range 0 through n inclusive, return the only number in the range that is missing from the array. So let's map this problem statement to the example. We're given an array nums containing n distinct numbers, right? We do have distinct numbers here in the range 0 through n inclusive, right? But what is actually n here? N here seems to be the length of the numbers in the array, so they mean 0 through n, which is the length of the array 3, inclusive numbers. So we return the only number in the range that is missing. The only number in the range that is missing is 2. N equals, n equals 3 here since there are 3 numbers. So all numbers are in the range 0 through 3. 2 is the missing number in the range because it does not appear in nums. There are 2 numbers in the array, so n equals 2, meaning the range is 0 through 2 inclusive. 2 is the missing number in the range again. We have n equals 9. Since there are 9 numbers, missing numbers in the range 8. N is equal to nums.length, and we'll always have at least one number. All the numbers of nums are unique. Could you implement a solution using constant extra space and linear time complexity? So I think you could. I think the key here being that the array contains n distinct numbers. Since you have n distinct numbers, it means that your sum will be since you have n distinct numbers in this range, we know that our sum is going to be a little bit deterministic. So if our numbers are 0 through 3, we're going to have this as our range, which means in our perfect array where only one number is missing, right? If no numbers are missing, our sum should be 6. So if we sum the numbers in the array, in this case 3, 0, and 1, we get 4, right? And if we do 6 minus 4, we get the missing number, which is 2. And so this solution would take linear time, right? Because we would need to summate the series are going from i equals 0 to nums, right? Inclusive, right? And then linear time again to summate values in nums array. And this should be nums.length. So this would be O of 2n time complexity with constant space. But we can do a minor optimization with the Gauss formula, which allows us to calculate sum of a series in constant time. And the solution for, or the equation for that, I believe, is n, right, where n is the, we can create a variable called n, which would be nums.length. It should be n times n plus 1 over 2. And so we can check. We have n, right, in our first nums array, which is equal to 3. So if that's the case, right, we can do 3 times 3 plus 1, which is 4, right, which equals 12, over 2 equals 6, which is exactly what we're looking for. And then here we'll say sum is going to equal to a reduce function, right, which just adds all the numbers together in the array and gives us a sum. And then at the end, what we can return is the math.absolute value of the Gauss formula and the sum together. So the solution there is actually linear time with constant space, because we're just doing one linear iteration over the sum of the array. So we have some notes from our previous time doing this problem, and one of them is, how does sorting simplify the problem? So let's read the problem first and then think about this. So given an integer array nums, return all the triplets nums sub I, nums sub j, and nums sub k, such that I does not equal j, I does not equal k, right? So I is not equal to j or k, and j does not equal k. So it means all of them are different. But also nums sub I, j, and k equals 0. So we notice that the solution set must not contain, duplicate triplets. So let's map this question here to our example. So we have this array of numbers which is not sorted, right? And the sum, right, we want to return all the triplets such that they sum up to 0 and all the indices are different. So I have -1, -1, 2, -1, 0, and 1. Both of these sum to 0, which is what we're looking for, which makes sense. Now I have nums sub 0, nums plus 1, nums 2, and -1 plus 0 plus 1 equals 0. Right, so we actually have two versions that produce duplicate. We have two versions that produce duplicate answers. And we can see that a duplicate number here is actually caused by, so the 0 is -1, 1 is 0, so up to index 4, 0, 1, 2, 3, 4. So we see that our duplicates are actually -1 and index 4, which are index 0 and index 4. The distinct triplets are -1, 0, 1, and -1, -1, and 2. So the order of the output and the order of the triplets does not matter. The only possible triplet does not sum up to 0. It's important. Input nums equals 0, 0, 0. The only possible triplet sums up to 0. So that makes sense, and we'd like to keep one of that. So our constraints, we know that in our nums array we'll have at least a minimum of 3 elements, and the range for the numbers ranges quite a bit. So questions from the last time we did this: how does sorting simplify the problem? What is our BCR? So our best conceivable runtime. We know that in other two-sum problems that there's one solution where you can find there's one method of finding, given an array, 2 numbers that sum up to a particular target, right? And there's 2 solutions to that, one which takes linear time as well as linear space, and there's also another version which takes linear time, or I guess n log n time, but requires that the input is actually sorted first, but it takes constant space. That being said, if our best conceivable runtime is, our potential best conceivable runtime is if two-sum runs in linear time, we have to do this for triplets. It's safe to assume that we could probably do this in n squared time with our two-sum implementation. And what do you get if you subscript an out-of-bounds array in JavaScript? You actually get undefined. So there's a previous thought of mine that if you subscripted an out-of-bounds array in JavaScript, you'd actually end up with an error, like a big issue. You actually just get undefined, which is pretty important. It allows you to know that you can check if an index exists in an array and then continue working with it. How can we get to n squared runtime? So I think one way to do this, right, if we want to generate all triplets, right, there's one method which we could use, right? So if we know that given 2 indices, we just have to find a sum to a particular number, then 3 numbers together, right, doesn't necessarily change that format very much. And what I mean by that is, if we know that, right, given an array, right, and a target, right, we know an algorithm to find the indices which will sum up to those values, right, indices 1 and 2 here, then all we have to do to include a third number is just subtract it from 0, right? Because the goal is we're looking for numbers that sum to 0, right? If we start at a particular index in the array, like in this array 1, we can do 0, right, minus 1, which gives us -1. Right, now we can run our original algorithm, right, through the array, right? What we're looking for is 2 indices, right, that we can add together to give us 0. What we find is that that doesn't exist, right? But if we add a 0, right, we'll see that it does exist. We can return 0 and 1 as our indexes, or I guess, yeah, 0 and 1 is our indexes to sum to 0. So it's -1, 0, and 1 sum to 0. The only problem with this is there's a deduplication process, which is important, right? The way we could make the previous one work would be n squared time, basically, right? Because we would iterate through the array, right, and then run a two-sum algorithm. If we're going to iterate through the array and run a two-sum algorithm, that's going to be n squared time, pretty much, since we're iterating through the array, and the two-sum algorithm also has to iterate through the array, right? But we would actually be we'd also technically, let me search something up. So we can actually still go for we'd actually be going for an n log n, or our sorting would technically bound us with a n log n time complexity, right? Because the prerequisite for this two-sum algorithm, right, that works in linear time with constant space, is that the solution space is sorted. So we'd have to do that, but in the end, our two-sum operations, worst case, time complexity, and best case, since we're generating all possible triplets, would actually be n squared. Right, so then we'd have all these triplets, right? And so how would we deduplicate them? So one thing what we could do going through, right, we want to avoid duplication. So if we were to take this array here and sort it, right, we'd have -4, right, we'd have an extra -1, right, that we want to move up here. We'd have 0, 1, and 2, and then it would be sorted. I think what we see is that if we start with a particular number like -4, subtract it from 0, right, we're looking for two numbers that sum up to 4 to give us that golden triplet that we're looking for, right? So we don't find any, but we go to -1, start at -1, we're actually looking for two numbers that sum up to a particular value to give us the two numbers that sum up to a particular value to give us the sum of 1, right? And there's 0 and 1 here, right? We actually is the only that would be the main triplet, right, that could do that in this array. We see that we actually end up with two triplets here, but we want to deduplicate them because not based on their indice, but actually, yeah, based on their indices, right, and their numbers, right. We don't want them to be the same. Oh, no, that their indices are different, that they're three separate numbers, but that they sum up to 0. So the problem is, once we go to this next array, we end up generating the same triplet. So I think what we want to do is, sorting also helps us to deduplicate. Sorting also helps us to deduplicate, because another thing it helps us, right, with is we can actually skip duplicates by just skipping sources, right, or target numbers that are the same as the target number we just processed, right? So we just did -1 here, right? All the answers are going to be the same, right, if we use this -1 here. So the next time we run this, we want it to be different than the current value. Right, and so we can say iterate through the sum of the array, right? Right, and then two-sum algorithm if cur num, right, does not equal last num, right? So if -1, right, does not equal, so, and this is why it was important to talk about the out of bounds JavaScript array. Right, if we look at the number behind us, right, no number exists, which means they're different, which means we actually do want to do two-sum algorithm, right? Same here, -4 and -1 are different. But as soon as we get to -1, we don't want to do it because they're the same number, right? And that's a problem. The next time we'd like to do it is when we're at 0, right? And so we'll say if cur num does not equal last num, then two-sum algorithm. And I think that if that doesn't remove all the duplicates, what we could do is implement a set, right? And since our output is sorted, right, the relative order among the main index, right, left and right should be set in stone. We can add those to a set and make sure that we deduplicate them. So we can jump into implementing that. So we're going to say for let I, right, is equal to 0, I is less than num stop length, right, I plus plus, right, and cur num is going to be num sub I, right. So we're going to say if nums sub I, right, does not equal last num. And it's not even that I think it's the last number. Well, yeah, we don't want the numbers to be the same. right, or the indices that spawn the numbers to, well, actually that's actually not what they mean, because the numbers that spawn the same sum are actually this different indices, but it's different total numbers. What they mean is num sub I does not equal num sub j, num sub I does not equal num sub k, and j does not equal k. So we'll say, well, num sub I does not equal num sub I minus 1, right? Then we want to run this two-sum algorithm. Right, we're going to have an output array which we're going to return. And another version we could just call this is triplets. I have triplets up here, which is going to be an array, empty array to start. We're going to want our two-sum algorithm, which is going to generate all the possible duplicates for this particular indice. And the I minus 1 actually ends up being okay when we start at 0, because it'll be undefined, and undefined would not equal I, which is perfect. Now there's two things that I'm worrying about, right? We only want to run this if they're not the same. So if we sort, it'll work like this, right? We'll start at 4, we'll generate nothing. We'll start at -1, then we'll generate -1 and 2, right? And then also 0 and 1, which would be the two values that we wanted. Or if we go to this -1, the values will be the same, so we'll skip it, and then we go to 0, right? And we shouldn't be able to generate one more. So let's try and implement this, right? We'll say triplets equals two-sum, and we'll pass in I to start, right? And the array of numbers. This function two-sum, right, is going to take idx, which is going to be a number to start, and nums, which is going to be an array of numbers passed in by reference, and it's going to return an array of triplets, basically. And so we'll say triples equals this array. Eventually we'll return triples, right? Which basically means right now that it's now possible for this value, right, to return an empty array. And so we're going to say if triples dot length, or I guess two-sum groups, it's a better variable name. We'll say if two-sum groups dot length is greater, right, than 0, then we want to do triplets dot push the spread of two-sum groups into the array, right? And so we're going to have a main number, right, which is going to be nums sub idx to start, right? And our range is actually going to be the current index, right? So we're going to say let left equal idx plus 1, right? And let right equal to nums dot length minus 1. And it's basically going to look a little bit like a binary search, but this two-sum algorithm allows us to find the target number that sums up to the number we're searching for in linear time by sliding up the left and right pointers. So a better version might be named first number. We'll have left and right, and we have to generate the complement value that we're searching for. And this target number is actually going to be 0 minus first, right? So we're looking for the number that sums to 0, right? We're starting at this array here with -1, right? We do 0 minus -1, which gives us 1, which means we're looking for two values that sum up to 1, right? And the -1 plus 1 will give us 0. So our left is less than right, right? We're going to say sum is equal to first plus nums sub left plus nums sub right. We're going to add all these three numbers together. We're going to say if sum equals 0, which is our goal number, or then we're going to say triples dot push, right, this array of tuples, which would actually be idx. And they didn't want the index. I think they wanted the actual sums of numbers. Yeah, the sums of the actual triplets. So say triples dot push first nums sub left triples first sub left, nums sub left, and nums sub right. And nums sub start. So I have triples dot push first, nums sub left, nums sub right. Right now, what if sum is less than 0? Right, if sum is less than 0, then we also want to jump that too quickly. We do triples dot push. We have to be careful to end up in an infinite cycle here because this is a while loop. Right, so let's say we find a goal triplet, or we have to make sure that we still keep finding more, right? If we set it equal to 0, we'll actually just keep evaluating back to our sum is equal to 0 on every iteration. So that sense, we're going to want to force a progress step, and that step can be left plus equals 1. And then we'll say else if sum is less than 0, right? If our sum is less than 0 and our input is sorted, it means that the smallest way we can actually increase our value is by moving our left array, which is from a sorted standpoint our smallest value. We can increment it to increment our sum. Also, if we do sum is greater than 0, right, that means our value is too big, right? And we have a left and right pointer, right? If we increment our left pointer, the value actually gets bigger. So it's it has a bit of an inverse aspect that way. If we do right minus equal 1, our value actually gets smaller. And so that works there. And so let's see if our assumptions make sense. And before we run the code, just make sure it makes sense in our heads. A simpler example. Right, we'll have -4, -1, -1, 0, 1, and 2. Triplets will be empty to start. We're going to start at I equals 0, right? We're going to say, is -4 the same as undefined? It's not. So we're going to do 2 sum of I, right, which is index 0, going to nums.length. Right, so our first number is going to be -4, right? Left is going to be equal to idx plus 1, right? It's going to be equal to the last element, right, which is 5. 1 is less than 5. Well, there's no numbers here that should sum to 0, so we actually end up returning an empty triplet. We push nothing. Then we go to -1, right? Does -4 equal -1? No, so now we want to call 2sum starting at index I, which is index 1, with nums.length, right? We go in, right? Our left is going to be 1 plus 1, which is going to be 2, 2 going to index 5, 2 is less than 5, right? And we're going to check, right, for our particular value, does -1 plus -1 plus 2 give us 0? And it does, so we're going to do triples.push, right, and do left plus equals 1. So now our left is going to be 0, right, and does -0, 0, and 2 give us 0? No, right? What does that give us? -1 actually gives us 1, which is greater than 0. Since we're greater than 0, we're going to do right minus equal 1. So now we're going to have -1, 0, and 1. Does that equal 1? Yes. So we're going to push 2 values on, get those 2 triplets that sum up to it, right? Then we're going to say, okay, go to the next iteration. We're going to push that on the triplets, right? Does I, which is -1, equal -1? Yes. Go to 0. Are they no longer the same? Yes. So now we can do one more iteration, right, where 0, I, and 2, right, and this cannot equal 0. So another thing I'm noticing, right, is if our sum is equal to 0, if our current number is equal to 0, or if our current number is greater than 0, our current number is greater than or equal to 0, and our input is sorted, there's no possible way that a sum could equal 0 because we're sorted. If we're here and our number is 0, the numbers after us couldn't possibly take us to 0. I think we can actually go even further. So if nums.I does not equal nums of I minus 1, and num sub I does not equal 0, right? When our number is not 0 itself, we can use this number to equal 2. But if we get to 0, there's no way that we could sum to 0 looking ahead in the array. So if num does not equal I minus 1, and num sub I does not equal 0, then we're definitely not going to find what we're looking for. So we have an error on line 20. So we are pretty much returning an array of any. We want to return an array of numbers. We'll be more explicit there in line 34. They're saying, right, argument of type number is not assignable to parameter of type number array. This is line 34. Argument of type number is not assignable to parameter of type. Oh, I sent in nums.length. We meant to send in was nums. Now we have a new error on line 11. Argument of type number is not, oh right, we said this was a number array. This is actually going to be a sort of a matrix, but it's going to be an array of number arrays. We forgot to update the function output. So it works with this first example. Let's try this test case here. Works for this one. Let's try one with all zeros. We should only run this once, starting from the beginning, and then skip every other iteration. So we actually produce no output here. So I wonder why that is. And we said num sub I does not equal 0. So I think what I'm seeing, I think I understand what I'm seeing here. Num sub I. I think what we want to say is, and num sub I is greater than 0. Oh, we want to change this to when we actually do the work. So when it's less than 0 is when it's possible that our sum at a particular number could equal 0. If we're greater than 0, it's not really possible to get there. Oh, if we say less than 0, then we still don't have output here. If we say less than or equal to 0, then actually that still works because we should still run once. So when we have all zeros, we'll say num sub I, we run once. I think I see what's happening here. Our two-sum function doesn't have the same skipping methodology, because in here, before we start the two-sum function, we make sure that the two numbers are different, right? And they are when we start, right? 0 is not the same as undefined, so it pretty much creates these two pointers and continues to check. The problem being that while left is less than right is not enough, we also want to skip the same mistakes that we also want to pretty much duplicate this logic here on 33. Right, and saying like, hey, if left, while left, not while left is less than right, but additionally, before we calculate our sum, we want to make certain that I just had it. We're not performing the same skips. So we do move left forward once, but it doesn't actually prevent us from not revisiting those values. So when we push a triplet, right, we actually want to push left plus equal 1, but also while num sub left, right, equals num sub left minus 1, right, we're going to want to also do left plus equal 1, right, because we move it forward once, right, we check if they're not the same, we move it forward again. But if every time we're about to try our next iteration to generate another triple and it's the same number as before, then we can't generate a new triple without creating a duplicate. So let's try it with our original example here, and then we'll try it with our new example. So here we're seeing that we have 404, negative 413, negative. So we're actually missing some groups. Negative 314, I actually don't see here. One, two, three, four, five, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7. So we're missing 2 groups here. I'm wondering if it's because of code we just added. Well, let's try it. If we add this as test case input, then remove these lines, so we 3, 6, 9, 11, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we end up generating 2 more, with the negative 314 still not existing. So that must not be the issue. Wonder if it's this portion with less than or equal to 0, but it shouldn't be. No, yeah, I'm just guessing a little bit there. I'm thinking that it could just be with the method in which we're generating the triplets. We push left forward plus 1, right? If sum equals 0, because this is what we actually want. That's why left is less than right. Oh, I think I'm seeing what's happening here. Wait, if sum is greater than 0, if sum is greater than 0, so we have 3 as a sum, right? We'd like to decrease our value. We can do that by doing minus equal 1. Sum is less than 0. Right, so this makes sense as well. We're just not generating all possible pairs, which is interesting. Oh, I'm seeing what happened. We're checking if sum equals 0. We want to check if sum equals target. No, it's actually I guess we technically don't need, oh no, it's not right. This is not possible. If we do sum is equal to first times left, then it's impossible for it to equal target. Less than 0, left plus equals 1, right minus equals 1. Yeah, they just, let me remove what I just added. There's just quite a few that are missing. Also going to print the sorted array. Maybe if we take a look, we'll be able to see why that is. So at -1, right, would be different than undefined, so we'd work in this range. We want to pretty much get all triplets that would equal to 0. There's 0, 1. The first one we would get would be -2 and 3. But apparently to our output, it's actually -1, -1, 2, which actually does make sense, right? Then -1, 0, 1, then -2, right? 2, and then -3, 3, and then we actually don't find one initially there for another -1. The next one we'll have is, then these two will be the same, so we'll skip it. These two will finally not be the same, so we won't skip it. So then we'll have -2, right, 0 and 2 as a potential sum. And then -2, right, -2. I think that's the most you can do with Nick. They're saying -2, -1, 3, which is they're right. We actually never, do we ever generate -2? We didn't generate -1, -2, 3. For some reason, we're not generating all possible versions. So we're not generating -2, -1, 3. Why is that? It should at least be coming through as -1, 3, -1, 3, 2. So if we start at -1, right, we generate -1, -1, 2, so we move forward once. We should be able to generate -1, -2, 3. Interesting. I think I'm seeing why, because we don't necessarily decrease. If we wanted to be two different numbers, then we ideally would decrease -1 as well. We still aren't generating -1, 2, and 3. It's just very strange. -1, 2, and 3, we should be generating I think we actually want to, I'm thinking we actually want to swap, we want to swap these two. If our sum is less than 0, then the quickest way to increment it would be to do left plus equal 1, right? And if our sum was greater than 0, the quickest way to decrement would be right minus equal 1, which does make sense. So actually, so right minus equal 1 did not help us generate any more. Num sub I is less than or equal to 0, which makes sense because all the numbers that we could produce would be going from the negative numbers up to 0. So we produce -1, -1, 2, -1, 0, 1. So one word that missing is -2, 1, 3, -2, right? 1, wait, -2, right? -2, -1, -2, and 3. Which actually, if you sum these together, you get -1 plus -2 is -3. We'd say sum is equal to 0. Well, our sum is -1, which is 2, and 4. Our sum is greater than 0. If our sum is greater than 0, then we'd actually like to decrease 4. So when we start, we have -1, -1, and 2. That's actually a strange first outcome now that I think about it. -1, -1, and 2. I think I see the problem being that we end up decreasing past our number before it's possible to add up to it with the current numbers that we have. This method is better for finding a particular target, but not for generating all possible versions of a triplet. Now there is a version of it that could be possible. So I think we could we could generate all the ones we're interested in. I think if we remove this line, because we'd have more tries to generate them, this would give us more than what we're looking for, I think. 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I think the other thing we'd have to do would I think be remove this one, and then we'd be able to generate all the outcomes. Then we'd still require a manual deduplication process. Could we streamline the deduplication process? Well, what if we removed all duplicates? Remove all duplicates. What if we say nums? We'll keep nums dot sort. We'll say nums is equal to spreading nums into an array. Spreading nums into an array, creating a set from it, and then spreading that back into nums. This way we could remove the duplicates. All right, and this kind of messes up with our greedy version of generating all possible versions. So I think we should go with our original solution. Right, we need to dedupe our output. So if we check our output, it should all be sorted in ascending order just based on how we add them. So we run our code, all of our generated versions should already be pre-sorted, which they are. And so we can create a function called keyify, which would take and array of numbers and actually return a string. And I think what it could do is say R could return R dot map, right, num, right, n dot to string, which will give us an array of strings, and we join them by space to keyify them. And then we'd have a set called seen, right? And if we haven't seen them before, right, then we'll keep them in our final output. So we'll create an output array, right? And then we can do for const triple of triplets, right? Then we'll say const key equals keyify triple. We'll say if, right, if we've never seen this string before, or I guess this identifier, which is naming the tuple or the triplet, then we're going to do output dot push triple and then seen dot add key. We'll return instead would be output. Three, 1, 2, 3, 4, 5, 6, 7, 8, 1, 6, 7, 8, 9. So we're missing generated output. We can also remove this portion here. One, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're still missing one, which I think we have -1, 0, 1, -1, 1, 2, -202, -213. We have -1, 2, 3. We have -3, 1, 2. We do -303. We have -3, -1, 4. -3, -1, 4 is one we don't have. Basically, yeah, I see now that our toSum function doesn't generate all possible versions. I think it could. So yeah, some things. Yeah, I think we can tell our toSum function doesn't generate all possible versions of a. Does not generate all possible versions of what we're looking for. This one is an interesting one.